Okay, so for the majority of you who have not taken the exam yet, please remember that you have to be out of the testing center by 7 o'clock tonight. The last exam is given out at 6, but clearly you don't want to leave yourself just an hour to take this, so make sure you're in the testing center well before 6 o'clock. So you can be out and make it to your FHE by 7 o'clock. That's the goal there. So today we're going to start chapter 23, and the first two chapters of this new unit are a continuation of the last three, in that we're still talking about carbonyl compounds and reactions of carbonyl compounds. But in the first, in the previous three chapters, we focused on reactions where the carbonyl group was an electrophile. Right? We're very used to, at this point, we're very, very comfortable with and used to seeing carbonyl carbon as an electrophile having nucleophiles attack. But we can convert carbonyl compounds into nucleophiles at the alpha carbon. And those nucleophiles are known as enols and enolates. And so our next two chapters are going to cover the chemistry of enols and enolates. We're going to learn about their structures and learn about how to make them in class today, bases that can be used to form enolates. And then we're going to talk about kinetic and thermodynamic enolates. So on the board right here, I've drawn for you a generic ketone. And then this is the enol from that ketone. The enol is a tautomer of the ketone. That's a term we learned last semester that we'll revisit in a moment. And then we can also form the enolate. The enolate is the conjugate base of both the ketone and the enol. Okay, this is the conjugate base. If we remove a proton from the alpha carbon, we get the enolate. If we were to remove the OH proton of the enol, we would also get the enolate. And these species will both react with electrophiles at the alpha carbon to generate products where we have attached some sort of a functional group to that alpha carbon. Okay? So I mentioned to you that enols are tautomers of aldehydes and ketones. I've drawn that up here on the board. What is a tautomer? This is a term that we learned back in chapter 11 of last semester. What is a tautomer? Okay, Brady? Okay, it is a constitutional isomer. And then there's one other condition. Not all constitutional isomers are tautomers. For constitutional isomers to be tautomers, what relationship do they have to have? Think about where we first encountered the term tautomer. We were generating enols in chapter 11 by hydroboration of alkynes or hydration of alkynes. And then those enols were in equilibrium with the ketones or the aldehydes. It's basically an irreversible equilibrium because the ketones and aldehydes were more stable. But whenever you have an equilibrium between constitutional isomers, that's what makes them tautomers. So constitutional isomers that are in equilibrium with each other are known as tautomers. So I mentioned it just now, and we learned it back in chapter 11. For a typical aldehyde or a ketone, the equilibrium strongly favors the ketone or the aldehyde. So for this particular ketone, there would actually be two enols because this is an unsymmetrical ketone. We have two different types of alpha hydrogens. But in this case, we would have at equilibrium, we'd have greater than 99% of our ketone. And then combined of our enols, we would have less than 1%. Okay? So not much of an equilibrium in this case. However, there is a special type of ketone where the enol is favored. If we have a 1,3 diketone, also referred to as a beta diketone, because if we look at one of the ketones, this would be the alpha carbon, this would be the beta carbon. Having a second carbonyl at the beta carbon would make this a beta diketone or a beta dicarbonyl compound. The enol of a 1,3-diketone is actually more stable than the enol than the ketone form. Okay, switch that a little bit. Okay, and there's actually two different enol tautomers when we have a 1,3-diketone. We can have the hydrogen bonded to the oxygen on the left, or we can have the hydrogen bonded to the oxygen on the right. Okay. So in this case, we would have about a 3-to-1 ratio, 24% of our 1,3 dicarbonyl and 76% combined of the equivalent enol tautomers. So why are the enol tautomers of a 1,3-diketone more stable than the ketone itself? There's two reasons. Yes, Brady. Okay. We have a stabilizing intramolecular 6-membered hydrogen bond. Okay, so that's a stabilizing force. We don't have any OH capable of hydrogen bonding in the ketone. So that's one feature that stabilizes the enol relative to the ketone. Yes? They look like they're resonance structures. They're actually tautomers because the hydrogen is bonded to a different oxygen. We do have two tautomers. That's not exactly a stabilizing effect like having resonance structures, but there is one more feature. Yes, go ahead. Yeah, we have conjugation in the enols that is not present in the ketones. These ketones are too far apart from each other. They're not conjugated. We got an sp3 carbon in between them. But when we make the enol tautomers, we have conjugation between the carbon-carbon and the carbon-oxygen bond. So it's the combination of conjugation and intramolecular hydrogen bonding that make the enol of a 1,3-dicarbonyl compound more stable than the ketone. Okay? Question? It is not. So a 6-membered intramolecular hydrogen bond will be stable because that ring size is free of strain. So you get the bonus of the stability from the hydrogen bond. You know, that's worth 1 to 5 kcals per mole, depending on how strong it is. And you don't have any strain to counteract that. So it's no accident that is a 6-membered ring. Okay. So let's talk about the mechanism of tautomerization. And we learned it back in chapter 11, but we learned it in reverse from where we'll learn it in this chapter. So we learned it for converting enols to aldehydes or ketones. Okay, but because it's an equilibrium process, it's the same steps, just in the opposite direction. We do need either acid or base in order to promote tautomerization. So we'll start by drawing the mechanism in the presence of acid. Okay. Based on your knowledge of carbonyl chemistry at this point, you should be able to predict how a ketone is going to react with strong acid. What's going to happen? Okay, Brady? We will protonate the carbonyl oxygen. Okay, we've seen this before. Okay. And then that's going to leave us with water. How is this protonated ketone going to react with water? Any ideas? Yes. Okay, so the water can function as a base, deprotonating. So we protonated first on the oxygen, and then we've deprotonated second on carbon using our water. And that forms our enol. And then it regenerates our acid. So this process is catalytic in acid. If you remember, and hopefully you do remember, the mechanism of hydrate formation that we learned in chapter 21, we learned that we can protonate a carbonyl and that water can act as a nucleophile and attack the carbonyl carbon. So you might wonder, why are we deprotonating here? Well, both equilibria are operating simultaneously. If we have a ketone dissolved in aqueous acid, most of that ketone is going to be present as the ketone, but you have an equilibrium between the ketone and the hydrate. We know that equilibrium favors the ketone, but you're going to have less than 1% of the hydrate present. And then you have a separate equilibrium between the ketone and the enol, and you're going to have less than 1% of the enol present. Okay, so if you're wondering whether the water is going to attack the carbonyl carbon or deprotonate the alpha hydrogen, the answer is yes. It's going to do both. But today we're learning about enols, so that's why we're learning the mechanism for the formation of the enol. Any questions? Okay, let's look at the mechanism in base. So if we expose our ketone to hydroxide, what's going to happen first? Okay, we will deprotonate the alpha hydrogen. And that's going to give us a resonance stabilized species. We'll talk about that in more detail. That's going to actually give us an enolate, which we will talk about in more detail in a moment. And then we have our water. How is our enolate going to react with the water? Okay, in this case, the enolate's going to deprotonate our water, giving us our enol. And regenerating our base. So you'll see that we have the same two steps, we just invert the order. To go from a ketone to an enol, we have to protonate the oxygen and deprotonate the carbon. In acid, we do the protonation first. In base, we do the deprotonation first. Okay? And then if we were going to reverse the process, the order that we learned it in chapter 11, then we just reverse the steps, right? The acid would protonate the carbon, and then our water would deprotonate the oxygen. Any questions on our tautomerization mechanisms? Okay, so let's talk about the reactivity of our enols. So we've seen examples earlier in the class where minor contributors give us a clue as to how a species will react. And the enol is no exception to that. So the enol has lone pairs adjacent to a pi bond. Anytime we have lone pairs adjacent to a pi bond, we have the ability to draw a resonance structure. Okay, in this case, the resonance structure we're going to draw of the enol is going to be a minor contributor because it will have charges. Okay? So this is definitely a minor contributor, but it has a negative charge on the carbon. And so what it tells us is that the enol is going to be nucleophilic on that carbon. So we can react with an electrophile. We're going to abbreviate the electrophile just as E+. We can react with an electrophile, attaching a new species, forming a new bond at the alpha carbon of our enol, and then we would usually have some sort of a base present, usually the conjugate base of whatever was delivering our electrophile. But then that would allow us to get to our ketone, the ketone precursor to the enol, with our electrophile here, and then whatever conjugate acid we had. Okay? So the equilibrium between ketones and enols is unfavorable. Usually you have less than 1% of the enol present. But if you can consume the enol irreversibly by reaction with an electrophile, then you can drive the process through an unfavorable equilibrium, an unfavorable ketone to enol equilibrium, followed by irreversible consumption of the enol would give us this product here, where the ketone now had a new group attached at its alpha carbon, a new group that was derived from an electrophile. Okay? Any questions? All right, let's talk a little bit about enolates now. So enolates are not tautomers of ketones. They're conjugate bases of ketones. Let me raise this up just a tiny bit more. Okay. And so they're generated by deprotonation of ketones. Okay. So we take a ketone, we're going to treat it with typically a strong base, as we'll see in a moment. Okay. And this is a resonance stabilized species because we have a lone pair adjacent to a pi bond. So we can draw a resonance structure. Okay. So this is our enolate, resonance stabilized. Which resonance structure is the major contributor, the one on the left or the one on the right? One on the right. Why? Negative charge on the more electronegative atom. Exactly. So this is our major contributor. This is our minor contributor. We do have a carbon-oxygen double bond versus a carbon-carbon double bond. And we learned in ketone-enol equilibria that the carbon-oxygen double bond is more favored. But because this is a charged species, having the negative charge on the more electronegative atom is more important in terms of determining the relative stabilities. So the contributor, this is the major contributor with the negative charge on the oxygen, minor contributor with the negative charge on the carbon. Okay? So usually when we draw enolate formation, we draw it directly to the major contributor. So if I were to have drawn, instead of drawing this curved arrow to the carbon, if I were to have drawn it to make a carbon-carbon pi bond and then pushed the pi electrons onto the oxygen, I would have gotten directly to the major contributor. That's typically how it's drawn. We usually draw the major contributor because it's more reflective of the enolate structure, right? In the hybrid structure, the negative charge on the oxygen is going to be closer to 1. The negative charge on the carbon is going to be closer to 0. And if we look here on the screen, we have an electrostatic potential map of an enolate. This is the enolate from acetone. And we see that it's kind of green and yellow, right? The yellow is indicative of a smaller negative charge, a delocalized negative charge that's spread out. You see kind of a hint of red around the oxygen, whereas the carbon is more greenish yellow. So you can see that there is more negative charge on the carbon, but it is shared. And you contrast that to an alkoxide, where the negative charge is localized on the oxygen, concentrated on the oxygen. We have dark red in that case. So this electrostatic potential map here shows us the delocalization of the negative charge in an enolate, but it also shows us that the partial negative charge on the oxygen is closer to 1. The partial negative charge on the carbon is closer to 0. Okay? Any questions? So let's take a look at some pKa comparisons. So let's focus on the top 3 molecules in this table: ethane, propene, and acetone. Acetone is the most acidic. There are 2 structural features of the enolate of acetone that make it more stable, to make acetone more acidic than the compounds above it. What are those 2 features? And they're written in the table, so you can actually look up the answer. What are the reasons why the acetone enolate is more stable than the conjugate base of ethane? Okay, please. Okay, so you summed up both of the reasons in one. Number 1 is that we have a resonance stabilized conjugate base. Okay. But we have a resonance stabilized conjugate base in propene. We can see the difference in acidity between ethane and propene means that that resonance is contributing about a factor of 7 to the stability of the conjugate base. And then the second thing you mentioned in your answer is that one of the resonance structures has the negative charge on an oxygen. Whereas if we look at propene and the conjugate base of propene, both of the resonance structures have negative charges on carbon. So you're sharing the negative charge between 2 carbons, whereas with an enolate, you're sharing the negative charge between a carbon and an oxygen. And so that's more favorable, and therefore acetone is more acidic than propene. Okay? It's not quite as acidic as ethanol. The conjugate base of ethanol is not resonance stabilized, but we've deprotonated an oxygen to make the conjugate base of ethanol, whereas we've deprotonated a carbon to make our enolate. And so there's an element effect. We go back to chapter 2. Hydrogens attached to more electronegative atoms are more acidic in general than hydrogens attached to less electronegative atoms. In some cases, resonance can overcome that. In some cases, generating an aromatic conjugate base can overcome that. But in this case, it does not. We see that the alkoxide is more stable than our enolate, right? So our ethanol is a stronger acid than our acetone. And then down here, we see, of course, the effects of resonance on hydrogens attached to oxygen by seeing how much more acidic acetic acid is than ethanol. So our enolates are more stable than most anions on carbon because of the resonance and the fact that one of the resonance structures has a negative charge on oxygen. It does not make aldehydes and ketones more acidic than alcohols because of the element effect. As you'll see in a moment, there are some special types of ketones that will be more acidic than alcohols, but not a normal ketone. Okay? Any questions about this chart here? Again, it's not necessary to memorize the values in the chart, but to understand the relative positions of these compounds is important. So let's examine the so we know here the pKa of a ketone is right around 19. We can make enolates from other types of carbonyl compounds. So let's look at those types of enolates, and let's see if those compounds would be more acidic or less acidic than ketones. So here's an ester. If we treat an ester with a strong base, we can deprotonate the alpha hydrogen. We can make an enolate from an ester. So conveniently, we've drawn the enolate of the ester right below the enolate of the ketone. take a look at those two enolates. Is one going to be more stable than the other? And if so, why? Yes.
Would the ester be more stable because the oxygen in the ester would pull?
Okay. So oxygen is electronegative, right? So you could have inductive withdrawing of electrons. When we learned about electrophilic aromatic substitution back in chapter 18, we learned that an oxygen can withdraw electrons from a benzene ring by induction, but it can also donate electrons to a benzene ring by resonance. Which of those was stronger, the withdrawing or the donating? Is an OH or an ether an activating group for electrophilic aromatic substitution or a deactivating group? Let's hope you haven't forgotten this. Our final exam is cumulative, by the way. Yes, Brady. It's a donating group, okay? So you zeroed in on the right feature here, but the oxygen is actually donating electrons to the enolate. Is that going to make the enolate more stable or less stable? Less stable because it's negatively charged, okay? So the enolate of an ester is less stable than the enolate of a ketone. As a result, a ketone or an ester is less acidic than a ketone. The pKa of most esters is right around 25. So you have about a six orders of magnitude difference in acidity, 10 to the 6th difference in acidity between ketones and esters. Okay? We can also make enolate-like species from nitriles. We learned in our last chapter that nitriles can behave similar to carbonyl compounds. They do not have a carbonyl group, but these 3 bonds between the carbon and the nitrogen can behave similarly to a carbonyl group. So we can deprotonate alpha to the nitrile. And I'm just drawing the major contributor for you, which is going to be this cumulated diene structure with a negative charge on nitrogen. This is also resonance stabilized. I skipped the minor contributor. The minor contributor would just have the negative charge on the carbon and then have the triple bond of the nitrile. But I've drawn the major contributor of that species. So the nitrile pKa is comparable to the ester. It's right around 25. Okay? We don't have the donating effect of the oxygen, but we also have the negative charge on a nitrogen as opposed to an oxygen. You don't get as much benefit from having the negative charge on the nitrogen and the major contributor of a nitrile as you do from having the negative charge on the oxygen and the major contributor of an enolate. So those two features cancel each other out, and you have nitriles being comparable in terms of their acidity to esters. Any questions? Okay, so a special type of carbonyl compound is the 1,3-dicarbonyl. We already saw this in terms of having the enol be more favorable than the ketone. If we treat the 1,3-dicarbonyl, this compound has a common name. It's called acetoacetone. If we deprotonate acetoacetone with a base, I'm going to draw for you the minor contributor in this case. Take a look at this minor contributor and tell me, do you think the enolate from a 1,3-diketone is going to be more stable or less stable than a normal ketone enolate? And why? More or less stable? Okay, Trent?
I'd say more stable because the lone pairs are
Okay? Okay, the second thing you said is really the key there, is that we have two carbonyl groups to delocalize that lone pair into, to delocalize the negative charge. Right? We can move it on to the oxygen on the left. And then we could move it on to the oxygen on the right. So what we end up with is an enolate that has two major contributors and one minor contributor, as opposed to one major and one minor. So when you get two major contributors and one minor contributor, we've got the negative charge shared equally by two oxygens, and then we have a small amount of the negative charge on the carbon. So that makes the 1,3 diketone significantly more acidic than a normal ketone. The pKa is right around 9. Okay, about a tenfold difference, tenfold increase in acidity relative to, or 10 orders of magnitude increase in acidity over a normal ketone. So this is actually more acidic than ethanol. Right? If you look at our pKa table here, ethanol is 16, so it's more favorable to deprotonate the alpha hydrogen of a 1,3 diketone than it is the oxygen of ethanol. So the enhanced resonance in this case, with two major contributors and one minor contributor, is actually able to overcome the element effect of deprotonating an oxygen in an alcohol. Okay? Any questions? So we have another table showing pKa values for a variety of carbonyl compounds and nitriles because they're comparable. Again, we don't want to memorize these numbers. If you know the figures roughly, or kind of ballpark figures, it can be helpful to you. But the most important thing is actually understanding the hierarchy or the relative ordering of these compounds in this table. So let's make a few comparisons here and make sure we understand why certain compounds are more acidic or less acidic than others. Let's start with the amide and the ester. pKa of the ester is 25. We already went over that on the board. We see here the pKa of the amide is 30. Why is the amide less acidic than the ester? Okay, please. Okay. Nitrogen is more basic than oxygen. It's less electronegative than oxygen. So the lone pair in the nitrogen is donating its electrons to the enolate more strongly than the oxygen was. We had that over here with the ester enolate. So we know that the ester enolate is less stable than the ketone enolate. And then it stands to reason that the amide enolate would be less stable than the ester enolate because it has more electron donation to the negatively charged species. So indeed, that difference is reflected in this 5 pKa unit difference, or 5 orders of magnitude difference in relative acidity of aldehydes to esters. Incidentally, this is a tertiary amide. You can only make enolates from tertiary amides. You cannot make enolates from primary or secondary amides. Why not? What would happen if you treated a primary or a secondary amide with a strong base? Any ideas? Would you deprotonate the alpha carbon? What would you deprotonate? You'd deprotonate the nitrogen instead, right? You'd make a resonance stabilized species from deprotonating the nitrogen. That's not an enolate. So we can only make enolates from tertiary amides, right? So a tertiary amide is the only type of amide we'll see in a pKa table. All right, so nitrile and ester, we already explained why they're comparable to each other in terms of their acidities. We understand why a ketone's more acidic than an ester. This table is also telling us that an aldehyde is more acidic than a ketone. Why? Why is an aldehyde more acidic than a ketone? Think about the structures of the enolates. Yes? Okay. So we know that alkyl groups are weak electron donators. Again, something that we learned back from electrophilic aromatic substitution in chapter 18. So we've got a ketone enolate here on the board. And we have this alkyl group here that donates electrons to that enolate. If we make the enolate of an aldehyde, this alkyl group is replaced with a hydrogen, and that hydrogen is not donating electrons to the enolate. Okay? So an aldehyde enolate has a hydrogen in place of an alkyl group that would be there in a ketone enolate. So that hydrogen enolate, or that aldehyde enolate will be lower in energy, and therefore the aldehyde is a bit more acidic than the ketone. Okay? And then our 1,3-dicarbonyl compounds, they're all more acidic than our standard monocarbonyl compounds. And as we would expect, a beta diketone is more acidic than a 1,3-diester, and then a beta ketoester is going to be in between the two. Okay, so we should understand the position of the nitrile groups we do have to memorize, but the other ones we should be able to understand in terms of the differences between aldehydes and ketones, esters and amides. Any questions? All right, so let's talk about the kinds of bases that we would use to form enolates. So if we are generating an enolate from a ketone, right, we have an acid-base equilibrium here. The pKa of our ketone is close to 20, right? 19.2 for acetone. We'll just say it's close to 20. So if we want this equilibrium to be favorable, what does the pKa of our conjugate acid need to be? Greater than 20 or less than 20? Think back to our acid-base chemistry. Is it favorable to make stronger acids or weaker acids in an equilibrium? Weaker acids. So the pKa of our conjugate acid needs to be higher than 20 in order for the equilibrium to be favored. So let's look at a table here of enolate formation with various bases. And what we see is if we were to use hydroxide, alkoxides, even tert butoxide, which is our strongest alkoxide base, because the conjugate acids all are stronger than a ketone, right? You would get a fraction of a percentage of the enolate if you were using these bases. They're too weak to make that equilibrium favorable. With tert butoxide, you might get close to 10%, right? 18 is one less than 19. So you might get up to 10% of the enolate if you use tert butoxide. Sometimes this is advantageous. In chapter 24, we will learn of cases where you only want a small fraction of the enolate, and you actually want a large amount of the aldehyde or ketone in solution. Okay, so in some cases, these bases are advantageous. You'll also notice, it's not shown in the table here, but these bases are capable of fully deprotonating 1,3-dicarbonyl compounds. If we go back to the previous table, we see our 1,3-dicarbonyl compounds. The weakest acid is the 1,3-diester with a pKa of 13.3. Hydroxide is 3 orders of magnitude stronger of a base than this enolate. So we can use any of these bases, hydroxide and alkoxides, to fully deprotonate a 1,3-dicarbonyl compound or to make a small percentage of an enolate from a normal aldehyde or ketone. But if we want to quantitatively generate an enolate from an aldehyde or a ketone, a normal aldehyde or a ketone, not a 1,3-dicarbonyl compound, we need a much stronger base, and sodium hydride is one. We've seen that before. The one that's most commonly used is the one shown right here, which is called LDA, or lithium diisopropyl amide. Okay? So it looks like this. It's a negatively charged nitrogen with 2 isopropyl groups attached. And then we have a lithium as the counterion, okay? So it's a very strong base. The conjugate acid, which is diisopropylamine, has a pKa of 40. So this base is strong enough to irreversibly deprotonate, quantitatively deprotonate any carbonyl compound that you can make an enolate from, okay? In addition to being a strong base, it is a very bulky base. And this is important. This is very helpful for its properties. Why is it important to have a bulky base? Any ideas? Yes. Okay, if you substitute the word nucleophile, so the strong bases are also strong nucleophiles in most cases. And we've seen countless reactions of nucleophiles attacking carbonyl carbons. If we want to make an enolate, we don't want to attack the carbonyl carbon. We want to deprotonate at the alpha hydrogen. If we use a bulky species, we know that nucleophilicity is inversely correlated with size, right? Bulkier nucleophiles are poorer nucleophiles. So if we bulk this up, it's going to be a poor nucleophile, but it's still going to be a strong base because basicity is hardly affected at all by size, because all we're doing in an acid-base reaction is removing a proton. That's our smallest nucleus. So that process is much less sensitive to the size of the base. So the fact that this is bulky makes it non-nucleophilic. It means that you're just going to make the enolate. So we could take cyclohexanone, we could react it with LDA. We wouldn't even need to draw an equilibrium arrow because of the strength of that base. We would be able to quantitatively make the enolate, the lithium cation from LDA. I should mention that's the abbreviation for this, by the way. It stands for lithium diisopropyl amide, okay? And then you would make the conjugate acid, diisopropylamine, okay? So sadly, the word amide or amide refers to 2 things in chemistry. It refers to the carbonyl compounds we learned about earlier. Those are called amides. And then when you have a negative charge on a nitrogen, it's the same name, okay? So I don't know why they have the same name for 2 types of molecules. In American English, people typically refer to the carbonyl compounds as amides, and they usually refer to the anions as amides. Okay, so this is usually called lithium diisopropyl amide. In Great Britain, they call everything amides, so I'm not sure how they distinguish between the 2. But when I say amide, I'm going to be referring to the carbonyl compounds, and when I say amide, I'll be referring to species with a negative charge on a nitrogen. Okay? So how do we make LDA? Well, we can actually buy it. We can buy it in solution, but we can also make it. Sometimes we make it. And what we would have to do is deprotonate this nitrogen with an even stronger base. And that stronger base that is used is an alkyl lithium, typically butyllithium. Butyllithium is our most abundant alkyl lithium. We've done this reaction in my lab frequently. We use LDA all the time in my lab. And when we make it, right, sometimes the solutions are back ordered, and so we have to make our own butyllithium. And we simply make our own LDA. So we use our butyllithium. We get butane as our conjugate acid. It just bubbles out of the reaction mixture, so it's very convenient. pKa of butane is around 50, so this is a favorable acid-base reaction. So if butane is a strong, or if if butyllithium is a stronger base than LDA, then why don't we use butyllithium to make enolates? It goes back to a discussion we had just a couple minutes ago. Why would we not use butyllithium as a base to make enolates? Yeah, it's a strong nucleophile because it's not hindered. If we react butyllithium with aldehydes or ketones, it adds to the carbonyl. Right? We would need a bulky species to function as a base, and that's what LDA does. Okay? So this is a symmetrical ketone, cyclohexanone. Let's say we have an unsymmetrical ketone. Methyl cyclohexanone. How many different enolates could we make from methyl cyclohexanone? There's 2, because we have 2 types of alpha hydrogens. We could deprotonate the one on the left, or the right, sorry. Let me move this out of the way. Or we could deprotonate the alpha hydrogens on the left. Kind of squish these together here. Which of these 2 enolates that we could generate from methyl cyclohexane is more stable? Top or bottom? Top is more stable. We have the more substituted double bond. So this enolate is more stable than the bottom one. So we're going to refer to that as the thermodynamic enolate. Okay. Which of these 2 enolates is formed the fastest? And I'll give you a hint, it's not the one on the top. Very good. Good answer. This one, it's the kinetic enolates. It's formed faster. Why? Why do you think this is formed faster than that one? Less steric hindrance, right? I told you that basicity is not very sensitive to sterics, but it does play a bit of a role. Especially with a bulky base like LDA, it's going to deprotonate less hindered alpha hydrogens more rapidly than it deprotonates more hindered alpha hydrogens, okay? So we have a situation where the more stable product of this acid-base reaction is formed more slowly than the less stable product. This is the second time we've encountered this situation in class. Back in chapter 16, when we were learning about the addition of HX to 1,3-dienes, we had the 1,2 addition product as the kinetic product, but we had the 1,4 addition product as the thermodynamic product, or the more stable product. So this is the second case where the kinetic product and the thermodynamic product of a reaction are not the same. Okay? So we can obtain either the kinetic enolate or the thermodynamic enolate as the major enolate by selecting our base and our reaction conditions appropriately. So if we want to form the kinetic enolate, the first thing we need is a strong, bulky base. Okay? And typically that strong, bulky base is LDA. That's the most common one that we use. Okay? The reason we want a strong base is we want complete deprotonation. We want to generate 100% of our enolate. We don't want to have a fraction of our enolate and a large amount of the ketone remaining behind. Okay? So we need a strong base, and the fact that it's bulky is going to cause the difference in rates between forming the kinetic and thermodynamic enolates to be greater. Okay? Second thing we need is a polar aprotic solvent. Okay? THF is our most common polar aprotic solvent. It's a cyclic ether, looks like this. We need a polar solvent to make enolates because our reactants are polar. Our bases are salts typically, so they're highly polar. Our ketones are polar, so it has to be polar. But what would happen if we used a polar protic solvent? What if we made, yes, Trent? Exactly. A polar protic solvent such as methanol or ethanol would protonate the enolate and get us back to the ketone. That's not what we want in this case. And so we need a polar aprotic solvent. Okay? And the third thing we need is low temperature, which is usually minus 78 degrees. We've learned previously that that's actually a convenient temperature in the lab because we can make dry ice acetone baths. Okay? So what the low temperature will do is it will prevent equilibration. much like in the addition of HX to dienes, if we ran it at low temperature, we could prevent the less stable kinetic product from equilibrating to give the more stable thermodynamic product. If we make the enolate at low temperature, we can prevent the less stable kinetic enolate from equilibrating to generate the more stable thermodynamic enolate. So if we put all that together, we could take our 2-methyl cyclohexanone, treat it with LDA, lithium diisopropyl amide, using THF as our solvent, running the reaction at minus 78 degrees. And what we will generate is our kinetic or less substituted enolate. Okay? So on Wednesday, we'll talk about how we would favor the thermodynamic enolate. Okay? Good luck on the exam. If you haven't taken it already, make sure you get into the testing center sooner rather than later.